This little instructional video will demonstrate a little bit about how you can model veins in GEOREKA itself. For this, we're using a data set which only has assay data. So we're showing you a bit how the assay data is distributed, so you can see the trace lines of the drilling data, and the blue and green indicates the actual assay values. So what we can do in GEOREKA is to highlight the assay data that we want to capture, and then we can create selections on that data. So that's what we're doing here. We are creating a new selection. So means you need to select the data set first, and then we'll give this new selection a name. So we'll give it a name vein. And then with the data visible, so only the visible data, and that's where the threshold comes in as well, will be selected. So you turn the selection on, you drag using the left mouse click, drag over the data. So I'll just change the color here because the green is a bit hard to see, so I'll change that to the nice pink color, and we'll drag over the various intervals with the assay data. We do one at a time, so we'll taking a slow process. We won't do the whole data set here, just a part of the data set just for demonstration purposes, so you can have an idea of how it works. When you drag or when you create like a marquee selection, the little box that you're drawing in your 3D scene, it selects everything within that box, so even at various depths. So you have to be a little bit careful at times. Alright, so now if we want to use this data, we'll need to define a modeling area. I'll just take you through this again. So in this case, we'll have a dipping structure, so we're actually setting a dipped model extent or model boundary. I'll just adjust the values here to match what we're seeing in the 3D scene. So in the bottom right hand corner, you can see that there's a plunge value we can use to set the dip here as well. And we'll give it a name. Forgot to reduce the extension to match a bit better with the actual data, so I'll just do that quickly as well before we actually save it. There we go. So now it's all nice tight around the actual vein that we want to model. The reason why we do it just around the vein is that we can limit the whole extent, and all the operations will be a bit faster. If you do the whole project extent, you could do it, but you'll run into trouble time-wise, but also accuracy-wise. Alright, so the first thing you need to do to create this vein is actually extracting the hanging wall, the footwall points, and that was what we're doing here. So we'll take the assay data that we used just before to create the selection, and we'll extract the contact points, so the tops and the bottom points. Just defining the final surface that we want to create. So this is the top surface and the bottom surface, or specifying some basic parameters. And this is the most important part. So here we take that selection that we call vein, and we'll take the start of the intervals. Again, we'll use the manual selection, but in this case we'll take the end of the intervals, and we'll run this process. And there we go. We have a first estimate of the vein that we want to model. As you can see, it created two surfaces, the top and the bottom, or you can call a hanging wall footwall if you want to. And we'll have a look at the triangulation size. So with the default settings, the triangle grid size was set to 25 meters, which is a bit coarse for this project, so we'll decrease that a little bit, and we'll run that again just to see what it looks like. Yeah, this should be a bit better. And then turn on the triangles in a minute. See if everything sort of matches now. see little areas I'm going to have to fix up a little bit. So here what you can see is that we made a selection that doesn't fit with the other selections in the data set. I'll quickly correct this, and this is typically how you would do it in the software anyway. So you make a selection, you get an idea of what the service will look like, and then you adjust that selection. In this case we'll just remove or subtract the little selection that we had before, and we'll just rerun it quickly. And there you see that it's updated almost instantaneously. Now we could do it for different parts. So the next step, what we did here, set up a workflow to not only do the surface directly, but we'll also use the smooth and snap to surface to take some of the bumps out of the final surfaces that we've created. We've updated the selection a bit more. What we really want to do is then demonstrate how you can actually build a solid from these surfaces now. For this part, because we only did a partial selection, we'll reset the model boundary to just fit with the area that we've created the selection in. And the reason we're doing that is that we can actually take a very fine resolution now for this last step. Typically veins will be fairly thin compared to the project area, so you might be talking about a couple of centimeters to a meter, maybe, or maybe a few meters, but depending on the area size, it's usually quite small. So that's why we want to have whole area that fits tightly around the vein that you want to model, so you can actually use a very fine resolution. So with these surfaces that we've created, we can then create our solid. So for this we use the build geological domain. So we need to start off with an empty model, and what we need to do is to define the area each side of these bounding surfaces that we're going to use to see what's going to be cut away. So we turn on the show cut side, which will display in white. That's the side of the surface that will be sliced away. So we take an empty model, and then we use the surface to chop a part away. So we just improve the speed of the processing here a little bit. So we've just paused the actual processing, and practice will be a bit longer. But you can see what happened. So we have only part of the model now, which is only constrained by one surface and the model boundary. Now we'll take the second surface to create our final solid. So we need another build geological domain, take the output of the first step, and take the second constraining surface, and now this will be inside the vein. We need to swap the mesh side on this side. We'll run it. So we'll pause the recording for a little bit, so it will appear as if it's really quick, but in practice it will take a little bit longer to calculate. And here we have our solid from those two surfaces that we've created. You see there's a little hole in there where the hanging wall footwall surface start to pinch out. Also in the bottom right hand corner here you see the pinch out there as well. Other than that, you have a nice solid vein within the model area, showing you what the result of the triangulated solid will look like. We can then use this to evaluate with your actual assay values. In this case, we only have single column of data, so we don't have to select a particular assay, but you can select any assay value or any numeric data basically that you have in your drill set. Just use roughly the default settings. The range setting is the most important one to double check, based on roughly on the distance between our drill traces, we'll set it to 50 meters, which should be sufficient. It's just to give an idea anyway. Then we can run the RBF within this solid. We can have a look at the final result. So here we see the RBF the RBF evaluation on the grid within the solid. And we can play with the threshold a little bit and see what the values look like. So I'll just change the color setting so we get a better overview. So the thing to notice here is this bright red spot in the top right hand corner. So this is an artifact because there's not a lot of data. There's an artifact. There's some error values in the actual data set as well. So always be wary of when you're doing these interpolations to double check with the actual data. And then we can have a look at the average grade and the volume based on the actual cutoff values that we have. We can then get a bit of an idea of the average grade and average the volume at that cutoff range. Alright, this concludes this video. Hopefully you find it useful. Any questions, just get back in touch. Bye now.